Let me just bring that up. Thank you very much, everyone, for voting for what you wanted to see. Also, to let you know, I am doing another session Thursday, I think it is, of this Choose What You Want to Learn. So if you're available on Thursday when I'm running this, I am doing 2 sessions more. It's going to be a different audience for what they rank, but you can vote for something different if you want to see different presentation at that session as well. It's going to be the same list of topics, but depending upon who's in the room, it might get sorted differently. So there we go. Here's one I prepared earlier. I also mentioned to some people that LinkedIn, if you want to stay in contact with me, LinkedIn is the best way. This QR code will take you to LinkedIn. Additionally, if you just search for my name, my picture is on LinkedIn. I'm easy to find. There's a few other Jamie Gillespies out there, but not too many that are in Australia. But yeah, you search for me, you'll find me. Additionally, I would like to give credit and thanks. These slides were originally created by APAN61, and APAN61 opens their slides up and content under the Creative Commons license. Now, when I say it was created by APAN61, it was created by me when I was employed at APAN61, but they do allow the external continued use of the material. So there you go. So this slide deck is going to go through and it's going to examine what are DOS attacks, what are the different types, how do they operate, and then looking at, after an understanding of the different types of attack, the different ways that you can go through and do defense against DDoS attacks. This is technology independent, so we try not to use a lot of specific brands or companies or things like that, but you'll spot the different technologies in there and how that's used. So looking at DOS and DDoS. So in general, a denial of service attack is an attack against the availability. Remember, in security, there's confidentiality, integrity, and availability, the CIA. DDoS is a security attack because it's against the availability of a network and availability of the services and data on that network. A simple DOS is a denial of service. This means it's usually from one source. It can be sending a lot of traffic, but it's generally only from one source. And then, of course, the more common ones that we have today is distributed denial of service, or DDoS. This is where it's originating from multiple sources, and it's usually through resource exhaustion. Single DOS attacks can be resource exhaustion. You know, if I have a 1 gigabit per second internet connection and you have a 100 megabit internet connection, I can send more traffic than what your network can hold because I simply have more bandwidth than you. What you're going to most likely see for a DOS attack is where one source is sending something that crashes a system or crashes a service or makes a system unavailable through a vulnerability. That's the most common one. So not all DOS attacks are DDoS. DDoS are just the most visible because they take up so much network resources in one way or another. So the impacts of a DOS attack. So from a user's perspective, they see a DDoS attack as an outage. For some reason, the network is down, and I don't know why. It's somebody else's problem there. From a security team's perspective, it's a loss of availability. It's part of that CIA triad that we're trying to protect from security. From the business side of things, the DDoS is affecting the business financially. Usually, DDoS attacks are targeting networks that make money using the internet. And therefore, if they're not connected to the internet, they are losing that revenue. Think about internet service providers, credit card gateways, gambling, casinos, gaming. All of these systems are making money on the internet, and every second that they are not on the internet, they are losing that revenue. And something to think about for your own networks. What is the cost per hour of your network being unavailable? Now, of course, there's reputation damage that goes beyond that, especially if you're a network operator or a network provider. But just think about what is the cost for your network being down, and think about that as basically funding that you can have for DDoS defense. So DOS and DDoS, you can group this by traffic. We've got three different ones here. We're going to start off with bandwidth exhaustion. This is your very classical DDoS attack, where you have many hosts that are sending volumes of traffic to your network. This may be targeted across your network, or it may be targeted to one point on your network. But it doesn't matter, because that bandwidth is going to traverse all the networks to that final point that it's coming in on. This is generally going to be large amounts of traffic, whether it be legitimate traffic of legitimate requests to a website, or it's going to be junk traffic, where they're just sending random data that doesn't make sense, but it's large and it takes up that bandwidth resource. The next type of DDoS attack is a connection exhaustion attack. This is where they're not sending large volumes of data, but they're sending a large number of connections. Now, the connections can be as small as a SYN request, the three-way handshake SYN, SYNAC, ACK, sending a large number of SYN requests. It can also be other types of traffic that are coming in, such as hitting a web server. Web servers have a limited number of connections that they can serve at any one point in time. It doesn't so much matter about the bandwidth coming in, it's the capacity of that server or service to actually serve the number of connections. And once you fill up those connections with this DDoS traffic, legitimate users cannot connect to the service. And that can be for any type of service. I use web servers, HTTP as an example, but it can be any type of service that you're operating, including SMTP. And then, of course, the bottom one, targeted exploitation. As I mentioned before, this is usually for a non-distributed DOS attack or a single source DOS. And this is where they find a vulnerability and they're exploiting that weakness to either cause the system to slow down, crash, or hang, or cause reboots continuously again and again. Now, we can look at denial of service by layers and what the types of attacks are for different protocols. So here, of course, we have the OSI model on the left-hand side. I personally don't like using the OSI model because that's not how the internet works. The OSI model is a theoretical model that is not in practice on the internet at the moment, and I will die on that hill. The TCP/IP model is how the internet is working at this point in time, so that's the primary one that I try to look at. When we look at the bottom network access layer here, this is where we're dealing with Wi-Fi, Ethernet, fiber, copper, that sort of thing. The main types of attacks that you're going to see that cause a denial of service is Wi-Fi deauthentication or jamming attacks using the radio frequency spectrum. You're also going to have electrical interference. This can be on purpose or accidental. If you have fluorescent lights still and you run unshielded Cat5 copper next to it, that the ballast can actually generate high frequency and can interrupt your Cat5 Ethernet communication if it's not shielded. Little things like that. And then, of course, construction equipment. Construction equipment has this wonderful ability of finding fiber optic cable and cutting it, no matter where it is. You can have a field the size of a cricket pitch and have one fiber optic cable run through that field. You put a piece of construction equipment, it will find that fiber optic cable. It'll dig and it'll find exactly where it is. Funny joke on this. When I worked for the internet provider in Canada 26 years ago, there was a story that construction equipment were magnets for fiber optic, but we thought, surely that can't apply to every circumstance. There was a news report of one of those backhoe diggers, with the big arm on the back. It was put onto a flatbed truck for transport from one location to another. But its arm was just a little bit too high. They didn't bring it down all the way. So the arm was a bit high. When they drove it through the city, it actually had reached one of the overhead cables and ripped it down and had cut fiber optic. So construction equipment doesn't always cut fiber optic in the ground. It'll reach into the sky and rip it down and break your fiber optic out from the poles and everything. It happens. It's what we have to understand. There's not a lot of protection here. Shielded cable is one thing. Protected fiber optic is another down at this lower layer. Another thing, of course, to think about here is if you're running a data center and you have multiple fiber optic lines coming in, have it brought in on different sides of the building, so that if something is happening on one side of the building and it cuts the fiber optic, that it's not going to cut the fiber coming in from the other side of the building as well. Next layer up, the internet layer on the TCP/IP model. The protocols that operate at this layer, you have the actual IP itself, as well as ICMP and the routing information protocol, which shouldn't be used very much anymore. There's not a lot of exciting DOS attacks that happen at this particular layer, predominantly because it has ICMP and ICMP flood. I've been doing networking for long enough that I remember ICMP floods and when they actually were dangerous. Nowadays, you just can't generate the size and amount of traffic that would be needed. If you have 100,000 devices in a botnet, sure, you could do an ICMP flood, but it's not going to be as damaging as some of these protocols up higher that we're going to talk about later. So technically possible, but not the best from an attacker's point of view. From the transport layer here, this is where TCP and UDP are operating, and here we're going to be looking at the protocols themselves. The main thing that you're looking at here is an abuse of the TCP three-way handshake by doing a SYN flood. There have been improvements on this. Dedicated firewall and DDoS appliances can actually mitigate SYN floods in different ways, like with SYN cookies or other ways of keeping state of connections without keeping the connection open. But the general thing here is that you're going to send a whole bunch of SYN packets to start a connection. It's going to reply with the second part of the handshake, but then you never finish the third part of the handshake. This can be damaging because from a service perspective, the actual application, it doesn't see this halfway connection. This is largely handled by the operating system's TCP/IP stack. So if you're not monitoring down to that layer, you may not even notice a SYN flood is happening. The application sitting above the operating system layer just doesn't see connections coming in at any point. And last but not least, this is where the exciting stuff is happening up at the application layer. This is where you have all of the great applications that the internet and that everybody understands a bit better, and you're going to end up with great attacks. So any of these services that operate on UDP allow for reflection and amplification. And I'm going to go into that in more depth on the later slide. So you also have different types of attacks where what it does is it actually makes a connection to the service and then it keeps that connection open. Think of SMTP, for example. SMTP has some timeouts that if it doesn't see traffic, it'll close the connection. But the traffic that it's looking for can be very slow and drip fed. It will monitor and look for just individual letters being sent, not necessarily a whole command line, but it's just looking for letter by letter by letter. So you could drip feed it. You could say, hey, if a connection will time out after 1 minute, at 59 seconds, I'm going to send one more bit of information, one more character. And I'm just going to be very slow and keep that connection open. And again, these systems have a limited number of connections that they can keep it open at one time. So by doing that, you can overwhelm the application layer. You also have VoIP and SIP flood attacks, and of course, complex database queries. This is an interesting one that if a web application is written poorly and the database connections are written poorly, that you can actually, from a web application, do a complex search that causes the database to do a lot of work. And if you keep sending multiple, like not human typing, but actually have an automated system sending multiple of these complex search queries that can't be cached, you can cause the database to constantly be spinning and spinning and spinning, doing so much work that it can't service legitimate requests. And of course, with so many web applications being database driven for the backend, a lot of the web application can fail at that point in time. Now we look at some of the trends here for DDoS attacks. I've stopped a few years ago, but we can sort of get a gauge for how this has been going here. Connection exhaustion attacks are hard to track. We have been seeing some of them, from the big providers like Cloudflare and Akamai. Google, they've advertised that they have stopped a connection-based attack, and we see one of those down at the bottom here. But it's largely going to be bandwidth exhaustion attacks. These are most common, easiest to graph and see the effects of them. So we go back into late 2012. The largest attack at that point in time was a 60 gigabits per second attack. By today's standards, that's still pretty big. I don't have 60 gigabits of traffic on any of the networks I've operated. So that type of attack can still take a lot of organizations and even countries off the internet. Just 1 year later, not even a year later, 5 times increase, up to 300 gigabits per second. This was an attack against Spamhaus, one of those spam blocking organizations. We then go 1 year later after that, we've got a 500 gigabits per second against Hong Kong, Apple Daily, and PopVote. It was a bit of a politically motivated attack. We go 2 years later, and we've more than doubled. We're up to a 1.2 terabits per second sustained attack. This was an attack against the dynamic DNS company DIN DNS. They don't just do dynamic DNS, they were also running authoritative DNS servers for a lot of organizations that are out there. And when they got taken offline, all of the companies that relied upon them for DNS resolution also went offline as well. And this is a huge supply chain attack from the perspective of a DDoS attack. If you're having a single reliance upon a single DNS provider and they are attacked, you lose access as well. So diversity in DNS is a big one from there. A couple years later, an incremental increase to 1.3 terabits per second against GitHub. Then 1 year later, we then have a 1.7 terabits per second attack. We then go 1 year later after that, and we've almost doubled again. We're up to 2.3 terabits per second against AWS. This is where we then get into RPS. This is where RPS attacks were being a bit more popular, but also being advertised as being stopped by their cloud providers. So here we have Cloudflare in July of 2021, a 17.2 million requests per second sustained attack. So we're not so looking at the bandwidth capacity, it was the requests or the connections per second. The actual bandwidth could have been much less than that. And of course, we then go 2 years later and a huge increase, Google stopping almost 400 million requests per second. That is an incredible number of connection requests coming in. That said, there are reports that are showing that the average DDoS attack, like very average, not against these big multinationals, is between 1 to 25 gigabits per second, and they typically last less than 4 hours. Some of them lasting only minutes, and some of them lasting, 1 to 2 hours from there. Sometimes these DDoS attacks are being used short to cause a small effect, and then they'll email the organization afterwards and say, hey, did you see that 5-minute outage that you had? That was us. We did that. Pay us money and we won't do it again. If you don't pay us, we're going to do it and it's going to last longer. So if they don't pay money, they might do another DDoS attack and they might go for an hour. And then they'll email again and say, did you feel that hour? I bet that cost you a fair bit of money. Why don't you just pay us and we'll go away. We'll never come back. So this is basically DDoS ransom. A very popular group that doesn't exist anymore, if you wish to look up for the news articles, was DD4, the number 4, BC. And it was DDoS for Bitcoin. And the whole ransom attack was they do what I was saying. They do that short attack, then a longer attack, and they say, just give us some Bitcoin and we'll go away. And it's really funny because the email that they send out says, we have strong integrity. If you pay us money, we will not come back and attack you again. We promise we have good integrity. Meanwhile, they're ransoming you in the first place. So if you want to look up the history records of that famous group, DD4BC, quite interesting. So what do DDoS attacks look like? This is the best visualization that I could do at the time. I apologize if my animation skills aren't that great. So a simple denial of service attack. You have one attacker, you've got one victim. The attacker sends either valid traffic or invalid traffic, but they're sending some sort of traffic that is going to overwhelm the victim and not literally set it on fire, but cause it to do so much that it's not accessible to regular people. So this is a simple DOS attack. Very straightforward. When we move to a simple distributed DOS attack or a DDoS attack, we still have an attacker, but we have this botnet sitting in the middle. A botnet is infected computers, a large number of infected computers with remote control robot software. You're remotely controlling a robot. That's why they call it a bot network or bot infected computers. Bot networks can be small, tens of computers, hundreds of computers. The largest that people have observed have been upwards of like 500,000 computers in a single botnet. That said, it takes a lot to manage a botnet of 500,000 computers. Like, think about computers that you're managing at your own organizations. Now try and manage 500,000 computers, each one of them being software upgraded, viruses being uninstalled, other criminals trying to take over your computer and kick you out and trying to take it back. So it's a constant struggle. The system administrators for dealing with a botnet is incredible work that they have to do. But botnet, let's just picture it as 10,000 computers, for example. So the attacker sends one little command to the botnet. The way of doing that varies, varies greatly. Even Twitter posts can be a way of communicating to a botnet. But you send one little command to the botnet, and then the botnet executes whatever that command is and sends a lot of traffic. It can either be connections or it can be volume, but they send a lot of traffic. So imagine 10,000 computers at the exact same time hitting your network or hitting one of your servers with whatever type of traffic they want. That is a simple distributed denial of service attack. Now we go up to the big one. This is the modern day. This is how you reach terabits per second of traffic, is through reflection and amplification. So we still have our attacker and we still have our botnet. The attacker still sends one little command to the botnet. So this is all the same. What we have in the middle, though, is we have these middle servers. One of the examples that I'm using here is a DNS server, but in a later slide, I'm going to talk about the other services that can do this as well. But DNS is very popular for this. So here you have open recursive DNS servers. So these are DNS servers that allow a client computer like a laptop to connect to it and act as a DNS resolver. A properly configured DNS resolver is inside of a network, and only that network can talk to it. But here we're talking about open recursive. Open, meaning anybody on the internet can talk to this recursive DNS server. The bots are going to be sending a DNS query for a text record, TXT record of a domain that the attacker controls. I'm just saying evil.com. It's not a real domain name, it's real, but it's not real. So for this example. But not only are the bots going to talk to the DNS servers requesting this special text record, but they're going to spoof or forge their source address. And their source address is going to be the victim. So here, they send a lot of requests to the DNS servers. Now, the DNS servers, they don't know what that text record is, so they recursively go from the root servers down and they talk to the authoritative server for evil.com. The attacker has created a text record here. This text record, they send a small request. This text record is 4,000 bytes long. It's a very long text record, longer than any normal text record ever would be. So this means that they send a small request, what is the text record? And the reply is going to be 4,000 bytes sent back. Now that 4,000 bytes gets cached on these open recursive servers. There's not a lot of communication here. It's just the one request, and then they hold on to a copy of it. Now, because the source address was faked, the replies are sent to the victim. Now, these replies are 4,000 bytes large for each one of them. And this is how those large DDoS attacks are working at the moment. So you could have 10,000 computers. Let's just say, we'll go with one. You could just have 1,000 computers. And if each one of those computers has 1 gigabit per second of network bandwidth, you now have 1 terabit per second of bandwidth being created. Now that 1 terabit is only in this direction, it then gets multiplied. And the multiplication is based on how many DNS servers are being used, how many open recursive DNS servers are being used as well. So you can see that this can very quickly reach terabit levels. So what makes for good reflection? It has to use UDP. UDP is a connectionless protocol which allows you to change and spoof the source address, redirect traffic to somewhere else. What makes for good amplification is a service that allows a small request with a larger reply. And that difference is called the bandwidth amplification factor. So for example, here we have a request of 64 bytes generating a reply of 3,223 bytes, and that creates a bandwidth amplification factor of 50. So whatever amount of traffic comes in, 50 times is amplified on the way out from it. This is a chart of rough numbers of what the bandwidth amplification factors are. So for example, if we take DNS as an example here, DNS, depending upon how the requests are done, the domain name length and everything, you can get a 54 times amplification. Over on the right-hand side, we have NTP, the Network Time Protocol. Now, this is a large number, 556, 557 times. That is for an older version of NTP that had a vulnerability in it. Now, if you've patched that vulnerability or changed the configuration, then the amplification is actually much, much smaller. It's not proper. But there's a lot of these misconfigured NTP servers that are still on the internet. So it's quite possible you send a small request saying, which clients have talked to you lately? And when it replies with the list of all the clients that have talked to it. That's how it amplifies that traffic so much. Memcached. Memcached was an interesting one. When it was starting to become popular, people were creating these Memcached servers on the internet to speed up a lot of applications, but they were putting them publicly on the internet on public IP addresses with no firewalling or filtering or anything like that. And it also had a vulnerability at the point in time where you could actually, via UDP, upload a file and then request that file back again. So you could upload a 1 megabyte file So the initial upload would take a megabyte of upload, but then when you request it, you're just saying, give me file, give me file, give me file. So it's a small request with a 1 megabyte response, all via UDP. So huge, huge amplification that could happen from that. This is just a screenshot from Wireshark. This is nothing special. This is me just accessing normal domain names in a relatively normal fashion. So you can see up in the top there, you've got a standard query for 8888, and the query was 80 bytes long, and the response was 372. So right there, you can see that there's a 4.5 times amplification. The next one below that, you can see that I'm querying Microsoft for the any record. And the any record replies back with everything that you see here. So you can see that there was the NS record, the start of authority, the MX record, but then you can see these text records. So just simply by asking Microsoft.com for all of its text records, you get all of this traffic behind it. So from there, it's a 73-byte request, and I get 539 bytes in response. And that's without creating special text records. You can create text records that are much longer than these ones here. Again, 4,000 bytes long. So mitigation strategies. Mitigation strategies are going to be protecting services against exhaustion attacks. This is the first type of DOS attacks that we're going to look at here. So we're talking connection exhaustion attacks. One of the first things that you can look at is what are the tuned settings for your TCP/IP stack on your operating systems actually running the services. So not so much on the firewall side of things, not the networking, but the actual end services that are listening. Sometimes the defaults for these are holding connections open for 5 minutes. So even after a connection finishes, it's in a wait state for 5 minutes, taking up one connection amount of bandwidth or amount of memory on that operating system. Of course, there's also SYN cookies in that, different ways that you can then handle it without having to store the memory by doing the computation and getting the SYN packet to come back with a different number. You can also go through and configure service applications. Another one is vulnerabilities or misconfigurations in this service application that allow it to be susceptible to a connection exhaustion attack. One of these was an attack against a type of module in Apache. The way that Apache at the time was handling connections, you could actually overwhelm it and hold on to these connections and keep it open, causing it to fail. Nginx, on the other hand, was doing things in a different way of handling its connections and was not susceptible to the same vulnerability. So an easy way for a lot of people to fix up against the slow Loris type of attack was to take Nginx and put it as a reverse proxy in front of their Apache server, or just change Apache to run Nginx instead. Things have changed since then, but this is an example that if your application can't handle the connection-oriented issues itself, putting a reverse proxy in front allows you to then do the filtering and handle the connections more efficiently. The other things that you can do, you can implement intrusion prevention systems or DDoS filtering on your advanced firewall. These are some of those advanced features that I was talking about in the last session. You know, you can run an open source firewall, but what features are you going to have? Make sure that it has the features that you want. Even if your firewall doesn't provide DDoS attack protection, sometimes it's labeled as intrusion prevention. And there's different types of DDoS attacks that even just a basic IPS system can identify and block as well. Now, this again is at a single point and for connections, not for bandwidth. So things to remember as we continue on from this. For connections where you're dealing with a large number of connections, you may also want to implement load balancing. If your server can't handle more than 100 concurrent connections, you might need to have a scaling up system. either static of just running many servers or having it auto scale to spin up more services that it can then handle an increased load for a short period of time. And for web servers, you can also implement web application firewalls, either at the network or on the server itself. These web application firewalls allow you to inspect the web requests, the actual get and post requests, look for things that might be malicious or things that are being abused, and be able to do the filtering right at the request layer so that it doesn't go through to the actual web application sitting behind it. An example of a free one is Mod Security. Over the past couple of years, there's been other web application firewalls that have come out. Mod Security is one of the original ones, but it's just as an example. Mod Security is free on its own. You can pay for a corporate subscription for more service and faster updates, but you can run it for free itself. You can run it in network mode as a reverse proxy, or you can run it directly connected as a plugin module on your web server application as well. And of course, other things that you can do, you can install dedicated on-premise DDoS filtering appliances. This is where we're starting to get into the bandwidth side of things as well that you can look at. Dedicated on-prem devices has pros and cons though. Pros, low latency. It's a dedicated box, usually hardware, not even virtualized, fast network connections, fast field programmable gate arrays or ASICs chips on it. Gives you a high degree of control because it's a box that you are managing, you are controlling. If you put your TLS keys there for decrypting and re-encrypting web traffic, you have control over everything. It's not going out to an external party. The cons for this, it's a physical box or multiple physical boxes. It has a large capital expenditure up front, in addition to annual support licensing as well. There's also bandwidth limitations here. It's a box on your network. It's not going to give you more bandwidth than what you already have, so it can protect your bandwidth that you do have, but if it gets overwhelmed, then the whole network is overwhelmed. So there are some limitations. We'll see that on the graphics on the slides. Additionally, running one of these types of boxes does require some technical expertise. It's not a huge con. You can train up technical staff to manage that already, but it is something to think about. Graphics that I've got for installing a dedicated on-prem device here. Let me just bring up my laser pointer. Where's my laser pointer? There we go. Okay, so this is the type of very simple network. I'm not trying to do anything complex here. You've got your upstream provider, whoever that is. Let's say that you've got two upstream links. So you've got your two border routers here. You've got your two internal routers here. And if you're getting traffic that is malicious targeting a particular server, you can see that the red lines are showing that the malicious traffic goes through your load balanced external links, but then internally it's taking the shortest path to the server itself. So that's what's being burned here. If we duplicate this and we install a physical on-premise DDoS appliance, it's usually going to be in front of the target service in one way. So what we have here is the malicious traffic, the red lines. You can see it coming through. The malicious traffic hits the appliance, and the appliance does the filtering. So the target is not being overwhelmed, but depending upon how much traffic, your network might be overwhelmed. But again, this target down in here could be a web server that might only handle 100 megabits per second of active traffic, of active requests. You could be running a 10 gigabit network, in which case, yes, this device will protect that server from the traffic, making the service unavailable. But once the traffic is larger than your total bandwidth of your network, your whole network's going to fail. So pros and cons. Next mitigation strategy. This is where we're focusing more on the bandwidth exhaustion attacks. Examples here, proactive rate limiting. This is where you might want to rate limit on certain types of traffic that are mostly or only used for DDoS traffic attacks. For example, non-initial fragments. This is not something that is seen in normal traffic, but it is a very common way of sending large traffic through a DDoS attack. So rate limiting of non-initial fragments. DNS does things differently though, so don't apply this blanket across all your services, because of course you can cause some problems for your DNS on UDP, especially the large UDP packets. You might also want to rate limit from commonly abused or unwanted ports. You can look at source ports and destination ports and go, hang on, these are ports that are mostly used for malicious traffic, so we're going to put a rate limit. We're not going to block it, but we're going to put a rate limit on that to slow it down. You can also be reactive in your rate limiting. You might see an attack, you might have a DDoS monitoring system that actually will trigger up alerts by monitoring BGP tables and that. Or monitoring your connections through your system and setting BGP alerts. You can then rate limit the traffic, and you can maybe rate limit traffic or redirect traffic to less critical network locations. So this is a little bit of a routing decision or routing rate limiting, depending upon the type of traffic that comes in. This is useful if it's targeting one specific destination, but if they're going across your entire network, it's hard to protect from a shotgun approach. So the types of defenses that we're looking at here you can see we've got our simple network and our target. What we have over on the left-hand side is a triggering router. This is a router that's connected with BGP to your internal BGP routers on the inside, but it's not actually for routing traffic through it. It's just for triggering and signaling BGP changes. What we have here is when you detect the DDoS traffic, you can actually say, this target IP address, send traffic to dev null. Now, this is for an attack that is targeting one server or one IP address. The trigger router can trigger an update and say this /32, this individual IP address, black hole it, which means that the red attack traffic comes to your external routers and then sends it off to the dev null bit bucket from there. You do still have a lot of traffic coming over your external links. So those red lines are very real. They can overwhelm your network if we're dealing with a very large attack. If it's not a very large attack, what you're doing is sacrificing the target to allow your other computers and services to still be able to work on the internet. One step better is instead of just doing local triggering for remote black holing, is that you have an agreement with your internet provider, whoever that is, that your remote triggering can actually trigger to BGP on their side of things. So this allows you to go past your upstream internet connection links, and it allows you to trigger to the internet provider. This is not something that happens quickly. This is something that takes negotiation and discussion with your internet provider, and not all internet providers will want to do this type of a service with you. So it's something to try and work out in advance if it's possible. Then if you want to use this as a DDoS response, it makes it a lot easier at that point after everything is negotiated and configured. Your internet provider, though, I haven't drawn the lines here. They still have a lot of red traffic coming into them there. Oh, there it is. I do have the picture for it. So, these could be the botnets coming from ISPB, and ISPC. A lot of that traffic will still be hitting ISPA, but at least it doesn't come down to your connection. So if your internet provider has enough bandwidth, they can maybe absorb it, but you definitely don't want it coming down onto your network as well. Another thing that you can do is anycast serving. So instead of having your target down here, you have your target being replicated around the world and advertised by an anycast IP address. Then what happens with anycast is the traffic the closest to the anycast server for each server will go to that server. And because it's all by the one IP address that's anycasted out, they can't control, the attacker can't control to send the traffic somewhere else. They send it to the one IP and it goes to the local point. So here you can see the botnet on the right-hand side goes to that anycast target, botnet over there goes to that target. This allows you to take a large botnet of DDoS traffic and break it down into geographical chunks. So if it was 1 gigabit per second, but you had 100 servers spread around the world, you're now taking 1 gigabit per second or 1 terabit per second, dividing it by 100 and spreading that around. Each server hopefully being able to handle the traffic of that division of everything. What you can see for the next one here is very similar, but instead of just pure anycast, we're using these providers that do the anycasting as cloud scrubbing. So you'll see this in a lot of the popular services, of course, Cloudflare and Akamai and Imperva, all of these big services, they have these cloud scrubbing data centers. So not only do they do the anycasting for you, but they actually inspect the traffic. And when they detect the DDoS, they'll actually scrub out the DDoS traffic and allow the legitimate traffic to still go through. Now, what you're doing here, instead of having 100 copies of your server all around the internet, all around the physical world, what you're doing is you're having 100 data center locations that then are running GRE tunnels back to your actual web server behind it. So what you have is, of course, the DDoS traffic coming through here on the red lines. The DDoS traffic is scrubbed by the cloud DDoS provider, and the green dot is that clean traffic going over a GRE tunnel. Now, as long as your target IP address is not exposed and the attackers don't know what that is, as long as they're attacking the anycast address, this all comes in and works really well. But if they know that the target is down there, down here, and if they know what this network IP address is, they can avoid the anycast and go straight to the target network. That's a problem. So there's a lot of research being done both by the good and the bad side to try and find these origin IP addresses behind the anycast. And if they can find it, that's where they're going to attack. So it can be tricky, but yeah, see, hopefully it works well. Just one thing that I don't have, do I mention it on here? No, I don't mention it on here. One thing that we can look at, so this, I don't have a slide for it, so you'll have to ignore my hand waving here. This remote trigger black hole, there's actually a service out there that instead of just doing remote trigger to your ISP, you join a collection of networks all around the world that are happy to receive black hole requests from network owners. So you can only request a black hole for the address block that you control. But if you're getting a DDoS attack against that target IP address, you can do a remote trigger, not just to ISP A, but to ISP B and to ISP C and thousands of other ISP networks around the world and say, this one IP address is being attacked, please black hole it right at the source. And if you can block that, then that means that this red line would not exist anymore. It would be a black line. The attack traffic would come into ISP C, they would recognize that they received the remote triggering black hole request from your trigger router, and they would black hole that IP address destination right there. Again, you're burning that IP address. That service will not be available, but your network and your ISP's network won't be receiving the large amounts of bandwidth. So that's an interesting one. Let me just very quickly bring it up. Where's my mouse? This is something I've been thinking about, but I haven't put it onto slides or anything yet. The UTRS, Unwanted Traffic Removal Service. This is from a security organization called Team Cymru. This, I believe, is free and accessible for any network operators. You do have to prove that you operate an IP address block in a network, and you have to go through this process of setting up the BGP for remote triggering. But yeah, it's really interesting. So if you wanted to take a picture of this, Team Cymru up in the top left-hand corner, and unwanted traffic removal service, sometimes called down here UTRS or UTRS. It's a really cool service. So something to look at. Again, you're going to be black hole. It's primarily when you have a single service or IP address that's being attacked, and you're going to black hole it for a period of time, but hopefully the rest of your network stays active. So something to look at. And again, you know, it's one of those things that is free and accessible to you. If you haven't heard of Team Cymru as well, look around their website. They've got cool stuff that's available as well for free. They do have some paid services off to the side, but look at the free stuff. Really great. Beyond that, just while I'm talking of free services, Shadow Server. If you haven't heard of Shadow Server, that's another one to look at, which can help you with stopping your network being used for DDoS attacks outbound. Let's see if I spell that correctly. Shadow Server Foundation. So yeah, so if this is, if you haven't heard of Shadow Server, take a picture of this, go to their site and look through these services. They scan the internet looking for open services that are commonly abused protocols. So again, you prove to them that you run a network, usually by the autonomous system number or by IP address ranges. You prove that you operate that network, and you can sign up for these free email alerts of you're running an open recursive DNS server on your network. And of course, as we saw before, open recursive DNS servers are used by botnets to use your network as a DDoS launching point out to other places. But they do so much more. It's not just for DDoS, not just for open DNS servers, but yeah, really, really great and freely available. They take donations to operate the service open for all network operators of any kind anywhere in the world. So there you go. So just a little side tangent on that. So yeah, so that was remote triggering black holing using Anycast and the cloud-based DDoS scrubbing services. So on the end here, mitigation strategies. Protect your services from attack. You can use a combination of these things. You can use Anycast, you can do DDoS protection and intrusion prevention systems, and your overall network architecture can allow you to define how protected you are from different types of DDoS attacks. You also want to protect your services from attacking other people. Now, remember, we talked about rate limiting, which is a straightforward one. If you are sending out large numbers of connections, you might want to rate limit them because that could be an outbound DDoS attack. But the biggest one here is this BCP 38. BCP is the best current practices, bulletin number 38. This has been around for years, tens of years, decades. It's all about outbound filtering with source address validation. Because remember, when we talked about the DDoS attacks and we talked about UDP and spoofing source addresses does not happen for legitimate traffic anywhere, full stop. Spoofed addresses is only malicious. Knowing that, your network should never allow traffic out from your network that is spoofing source addresses that don't come from your network. Does that make sense? Now, if everybody did this, spoofed UDP DDoS traffic would not exist on the internet. But this is one of those things that you could implement this. You would have to spend the time researching it, implementing it, troubleshooting it, testing it, all of that. But it's not going to stop DDoS attacks against your network. So this is one of those ones that for the bosses in the room, this is not the time for you to say, what is the benefit to us? Well, there is no benefit to you. This is about the common good. This is about you not being a source of DDoS attacks against other people. And if everybody did it, DDoS attacks go away, or UDP reflected DDoS attacks goes away. If anybody has looked at the Manners program, the mutually agreed norms for routing security, I think that's how you spell it. This is one of the key points to being certified for Manners routing security. Next one down from there, securely configure your DNS, NTP, and SMTP servers. These are the most commonly abused protocols for doing DDoS attacks. They're all UDP based. They're all amplification and redirection attack. You want to make sure that you are protecting them as much as possible so they can't be abused for DDoS traffic. And of course, no open DNS resolvers. Remember, open to the internet is bad. Open to your network is normal and the way that it should be operating. So DNS resolvers should always have a limit on who can talk to them. And that's it. So that's my DDoS attack presentation. Did anyone have any questions that they wanted to ask on that? I've got a microphone here. Yeah. No, all good. One thing to remember, I will put it back up. Where's my slides? Link off to my LinkedIn QR code, or just search for my name. Best way to get in touch. I know it's a lot of information, but if you do think of questions later on, I'm here for the whole week as well. I'm going to be today. I'm dressed quite nice. I do wear very bright shirts later on as well. So if you do spot me, I'm tall, blonde, but I'm also probably going to wear very bright shirts, so you'll spot me quite easily. Feel free to come up, ask me questions, talk to me later on. My main work for this week is working with APAN and being here for this. I'm not working for a company for this week. My time and my brain is all here for this week. LinkedIn, way to communicate with me later on. The copies of these slides, if you go into the Orbit, either the web application for the agenda or the mobile app for the agenda, later tonight, assuming I don't go out partying tonight, later tonight, I'm going to take the PDFs of these and upload it into the Orbit system, so you'll be able to download the slides from there. If you don't see them for some reason, ping me on LinkedIn and I can just email you the slides and information as well. Additionally, there was all of these other topics that we were looking at. Where's my mouse gone? There were these other topics we're looking at. Come to my sessions on Thursday. If you don't have other things going on, you'll be able to vote. Hopefully we'll surface up a different topic that I can go through and talk about as well. But if you want the slides for any of these, please let me know. There's also some of these that have been previously recorded and are available as YouTube videos. So for past APAN conferences, the number 7 here, the vulnerability assessment and penetration testing, that's actually a very technical presentation with some hands-on and an online lab that you can go through and do. That one is recorded. So if you search for that exact thing with APAN in the search term, you should see the recording for that, as well as maybe some of the other ones. There should be a recording of password control. I love talking about passwords because so many things have changed over the years on what is a good password and what is a bad password, that not everybody is up to date on it. I also, in that presentation, break down the math on what makes a good password and why uppercase, lowercase numbers, and special characters, why that's not needed, down to math. Because when it comes to guessing passwords, it's all about a numbers game. How many guesses can you do per second, and how big is the password range that you're guessing from? So we're trying to make that as big as possible, and length is better than complexity. These ones up at the beginning, these are introductory modules. So security for services, I do have the presentation that goes through. I consider it a bit old because I created it probably about 6 or 7 years ago. But it does go through service by service, things to look at for changing the security on it. But it can be useful in one place. This one, threats and countermeasures to CIA. This is a shorter module. Actually, I might even be. We're going till 5 o'clock, right? 20 minutes. I might be able to go through. That number 3 is a shorter slide deck, so I might actually bring that one up. This one down here, email security. This was part of a research project that I did on the use of SPF, DMARC, and DKIM across the Asia Pacific region. So that's an interesting one, but I think the recording of that is online as well, if you search on YouTube for it from various conferences. But yeah, let me see if I can find threats and countermeasures, because I might be able to do that in the time that we have available. What do we got? Oh yeah, this is a small one. I'll be able to go through this one easy. A different color to make sure everybody stays awake. So as the slide says, I am still Jamie Gillespie. That is still my LinkedIn there. Everything there is the same. So threats and countermeasures for CIA. Again, as an introductory from security, I was talking about CIA in the past 2 topics that I was talking about here. And this is just breaking down what is CIA and why is this what security is based on. It's sometimes called the CIA triad or the CIA triangle. We're not talking about the Central Intelligence Agency of the United States, but we're talking about confidentiality, integrity, and availability. Almost all aspects of information security and cybersecurity comes down to protecting a combination of these things for every piece of information, architecture, and systems that we're looking at. Confidentiality, of course, is where we're trying to prevent unauthorized people or processes from accessing information. So the confidentiality is we're trying to maintain who can view that information. For integrity, we're trying to maintain and assure that the accuracy and completeness of data. Here, we're looking at data that could be modified by unauthorized people or processes. Now, I talked about that one in the last session before the coffee break, where we're looking at one of those future threats, where instead of people just coming in and ransomware encrypting your hard drives, they discreetly make changes to data that may not trigger alerts, and they can make your data untrustworthy into the future. And then, of course, availability. Availability on the strict definition here is ensuring that information is available when needed, but within expected bounds. And this is an interesting thing. From a network engineer perspective, you think of availability in the number of nines. 99.99% of the time it's up. It's 4 nines. Is it 5 nines availability? That type of a thing. But when it comes to security, not everything is about availability right now, this second. Now, I talked about backups in the last session. Take backups as a great example. You back up information onto a tape, you put the tape on a truck, and you send it to an offsite facility for storage. If you needed to restore from that tape, you know it's going to take time to find the tape, put it on a truck, drive it back, and put it into your tape carousel. You know that that's expected on how long that time is going to take. So the availability is still there as long as you can get it within the expected time frame. So it might be 2 hours in order to get the tape back on site and load it up for a computer to be able to access it. But as long as it's within that expected time frame, it's still considered available data. Not everything is about 99.999%. Now, beyond CIA, there are some other extensions. Some people are trying to make this larger triangle with extra letters. There's nothing standardized. As far as a universally accepted thing, it's that CIA triangle or triad. But we can add on a few extra things. One of them is non-repudiation. Non-repudiation is basically that the sender or the receiver of information cannot deny that they had sent or received that information. So one of them is cryptographically signing messages that you send out. If I have a private key and I use my private key to digitally sign a message that I send you, as long as I am the only one controlling my private key, any signed message is guaranteed to come from me, and I can't deny it because it's signed with my private key. On the receiving side of things, it could be read receipts or something like that to prove that you had received it. But I mean cryptographic read receipts, not whatever Microsoft is doing as read receipts. Another bit of an extension on confidentiality, integrity, availability that doesn't fall into other areas is safety. Now, safety has grown over time. Now, this is largely not in the strict sense of IT, but when you start looking at OT, the operational technology, you start looking at critical infrastructure like water filtration and water transportation plants, electrical generation and electrical transmission, air conditioning systems within a building. All of these things are operated using computer systems called operational technology, and sometimes they do connect in with internet technology and information technology as well. When you're starting to deal with these critical systems that are controlled by computers, we have to be thinking about the security of these systems, that it's not just protecting the confidentiality, integrity, and availability, but the safety of those systems as well, because they can impact on humans. Now take that to the next level. Self-driving cars. You now have a 1 or 2 ton vehicle that can be controlled over the internet going down the highway at 100 or 110 kilometers an hour. That can kill people, absolutely. And there have been vulnerabilities in these self-driving cars. They can disable brakes remotely. They can make it speed up. They can just fully control or disable components of the vehicle, causing any sorts of real human safety issues. So you have to look not just at the IT systems, but you have to look at the real world impact for a lot of them. And unfortunately, CIA doesn't cover it. So safety is sort of one of those extra things that can be added on to it. So looking at attacks against CIA. So we're looking at the common attacks against confidentiality here. So confidentiality is attacked by breaking through the protection layers to disclose information that's trying to be kept private. So examples here, a server might be compromised to extract a database of personal information. A prime example here, this was an interesting one. There was a website called Ashley Madison. This is many years ago. And the whole purpose of this website was for married people to have affairs. It was a dating website for married people. Now, obviously, people were using that expecting a certain level of privacy. They didn't want this information being made public. There was a weakness in the website. Attackers exploited it. They stole the database and published all of the personal records of everybody who had been using this service. This got so bad that people, there were government officials that were using this service, okay, married government officials, and you knew that they were government officials because they used their government email address to sign up to the service. So there was government employees that were being fired or were quitting out of shame for this. There was even some rumors of people that might have committed suicide because of the shame that they had for this information being made public. And of course, marriages were destroyed as well because they were having extramarital affairs here. So really interesting as an example of something that impacts people's real lives, not just the password to their Twitter account or something like that. Sometimes the goal is password databases. So it's not so much the personal information, but it's the passwords, type of personal, types of sensitive information. Password databases then can be extracted and decrypted, or passwords guessed from it. And if people are reusing the same password on multiple systems, once they get the password from one, the criminals can then use the same password to try and log into other systems that the user may have. And of course, your email address is your username. So once they know your username and the password, they just go and they try every type of service trying to log in for that. If you haven't seen the website, Have I Been Pwned? Really good for checking your email address if it's been involved in any of these password data breaches before. Attacks against integrity. So integrity attacks are usually for the modification of data or modifying pointers to data. You know, if you point to the wrong index, the data is essentially just as lost. Common examples here is website defacements. Website defacements are an interesting one. This has been popular for 25 years, probably when I first started working in information security. I started seeing these types of attacks. The criminals would break into a web server and they would change the homepage of the website. And they'd say, hacked by, Fluffy Bunny was a popular one 25 years ago. Whenever they would break into a website, they'd put up this picture of a Fluffy Bunny toy or something like that. And their hacker name was Fluffy Bunny. And it was basically a slightly non-destructive way of showing that you had good hacker skills that you could break into these websites. There's a website called zoneh.org that still is listed as like a scoreboard. So these criminals that can break into websites and change it, they put the information onto the ZoneH archive and they get a score record for how many websites that they have compromised. Yeah, really interesting. But of course, that's the sort of less destructive part of integrity attacks. The ones I talked about previously, those are the bigger ones. The small integrity changes to your data that you don't notice. Maybe they go into your Active Directory system or your identity and access management system, and they add in a user. Maybe it's got admin credentials. Maybe it's got, just down from admin. Would you notice if a new user account was created in your Active Directory system? Would you notice if a deactivated account was reactivated or a password changed? All these things could be backdoors allowing criminals back into the system. And of course, the last one is availability. Availability attacks is where a system is taken offline or inaccessible to legitimate users. This is the DOS and DDoS attacks. Now, I'm not going to read through this text because we just did the whole module on DDoS attacks. This is sort of a repetition of that, but we're looking at network availability from DDoS attacks. We're looking at server operating systems that are not being available from DDoS attacks. And of course, we're looking at the actual resources on a system that might be filled up from these DDoS attacks. Even to the point where you could have like a Bitcoin mining software installed on your servers. And if it's so aggressive on the CPU, it could actually use up so many CPU resources that your system is not accessible by legitimate means because it's being used for coin mining so much. So yeah, so what are the defenses for confidentiality, integrity, and availability? So for protecting confidentiality, it's all about the access control to make sure that only legitimate people have access to the information that they should have. Now, one of the other ways that you can do it beyond access control is encryption. Encryption is, of course, then protected by a key, whether it be a public-private key or a password. So if the criminals were to get access to encrypted data, they actually don't have access to the raw information behind it. So the confidentiality is still held as long as the encryption is at a secure level. This is one of those interesting things. Encryption is changing. We're looking at quantum computers being able to be developed over the next few years that will be able to break traditional cryptography in a shorter period of time. Now, when it comes to encryption, you want to make sure that your encryption can encrypt and protect the data for the life of that data. Say, for example, I have a credit card. My credit card number and the credit card is valid for maybe 3 years. I get a new credit card every 3 years. So any protection that I have on my credit card number needs to protect it for at least 3 years, expecting the speed of computers to go up over those 3 years. If I get a new credit card today and I encrypt that information today, 2 years from now, if that were to be broken, the credit card number is still valid. So not only do you have to project from now forward the life of the data, you also have to look at the competing curve of the speed of computers and the speed of encryption breaking. And it's not just 3 years that you have to protect. You have to sort of protect the extended time to combat the speed of computers breaking the encryption into the future. So this is why encryption is changing now, and we're looking at post-quantum encryption. If you're not starting to change your encryption now, you're not going to be protecting for when quantum encryption breaking computers become financially feasible and available. And remember, it's the life of the data. If you have data that is valuable for 10 years, not only do you have to protect the 10 years, you have to protect 10 years of quantum computer advancements. And most likely within 10 years, we're going to see practical applications of quantum computers that can break today's encryption standards. So encryption is great for protecting confidentiality, but make sure you're doing encryption properly. This is one of those little things that you have to really be ahead of the curve and be ready for changing to the next big thing. If you're not, then you're just going to be hitting a problem 5 years, 10 years down the track. For integrity, protecting integrity, we're looking for changes or preventing changes to data. Obviously, here some access control is going to be important. You know, read-only access prevents writing or modifying of data. But you also want to look for changes. Hashing, encryption, and digital signatures are also ways that you can be looking to prevent changing data or giving you an alert if the data has been changed. But again, just purely hashing the data is not enough. You need to then verify the data to the hash in the future on a regular basis to alert you when something has been modified. And what if something has been modified? What do you do then? You need to make sure that you have regular backups that are available so that you know the last known good hash and last good integrity of data was maybe 1 week ago. We need to restore that data from at least 1 week ago before it was compromised. And of course, availability. Availability can be through a number of things depending upon the type of data, systems, or networks that you're looking at. Of course, redundancy and high availability is straightforward. Don't forget about patching, though. Vulnerabilities exist that can cause systems to crash, and that is an availability issue. So by keeping your systems patched with security updates, that is protecting availability. You may need to increase resources, whether it be bandwidth, CPU, memory, anything like that. Good backups for availability, but also having disaster recovery and business continuity plans. Remember the layers that I talked about. Technical layers is not enough. You need to have administrative layers as well. You need to have that governance, the policies, the procedures that layer on top of it. Having just backups is not enough. You need to have that disaster response plan for when there's a larger event that needs a lot of recovery. And that's it. That's just a short little presentation bit, spot on 5 o'clock. Hopefully that was interesting for you. Again, this was a module that was an introductory one as part of a longer, like a 5-day training workshop, but breaking it down into little pieces. Thank you very much for your time. I will stick around here if you wanted to chat or ask me questions afterwards as well. But yeah, do feel free to reach out to me online. Look for me later through the week as well. Really enjoy. Oh yeah, sure. Do we have the microphone?
Thank you. So you were saying that once quantum computing comes, we understand that the private key, public key, cryptography will be over.
Certain levels of it will be broken, yes. And the thing is that when you're talking about encrypted content, is that there's something about store or read now, store now, decrypt later. So right now, if you could take any internet connection, say all the traffic going over the Wi-Fi right now, if you could capture a terabyte of that, you've got this big block of data, but you can't decrypt it. You hold on to that data, you put it on a hard drive, you wait 5 years in the future, quantum computing becomes financially viable, and you take that terabyte of data and you decrypt it. Suddenly you've got access to that information. So is the information that we are encrypting right now, using encryption standards of right now, is it going to be valuable information in 5 years? And will the encryption that we're using right now be quantum safe in 5 years? That's what we're looking at. So the whole point of going post-quantum encryption now is not because quantum computers now are working to that level. It's about storing the data now and decrypting it 5 years down the road. And that's the scary thing to think about, is that people right now, governments right now, companies right now are storing encrypted data to break it 5 years from now.
So that is applicable only for stored data. It's
Yes.
not like that HTTPS protocol will become invalid.
No. But when you look at HTTPS, we've gone through SSL version 2, SSL version 3, TLS 1.0, TLS 1.1, TLS 1.2, TLS 1.3. TLS 1.3 is the current active development with post-quantum encryption being put into there with cipher suites being added in. If you're not using TLS 1.3, then the HTTPS data right now could be stored and decrypted later. And this is where everybody has to play a part. We are both consumers of services and we are operators and network engineers and directors and managers of services. So when you're accessing your online banking, you hope that your bank is using a high level of TLS that is secure, but you don't control it. But the services that you run and operate yourself or that you manage within your organization, you do have control over that. So do what you can to protect the things that you have. And if you ever see other services not doing things at a good, best standards, best practice level of security, you need to be talking to those vendors. You need to be talking to those companies that you're using for personal and professional purposes and say, hey, I don't think you're doing enough for security, and put the pressure back onto them to do it. But yeah, everybody needs to be raising those levels of security. That was my other talk for SMTP. For email security, right now, email is very poorly encrypted from one server to another. Encryption is optional. So much email via SMTP is going around the internet 100% unencrypted right now. It's incredible to think about that your email is the same as a postcard, where you write your message on a postcard and put it into the mail, into the postal service, and anybody along the way can read your postcard because it's completely unsealed and unencrypted. But we don't see that traffic. So it's hard to understand it. That's why my other presentation on email security is so insightful, because it's raising that issue to people that normally wouldn't see it. But yeah, everybody has to look at encryption. You can't just say, I'm using HTTPS, because you could be using old encryption standards of HTTPS that are even weak by today's standard, let alone 5 years from now.
Okay, thank you.
No worries.
as you said, quantum technology or something like this. So I have one observation. Cloudflare protects website not to be protect from a bot attack, right?
Yes.
Few weeks ago, Cloudflare itself was out of service.
Yes.
So where is the end actually?
It's a very interesting thing. And this is the same thing with using cloud providers. Say you switch your email to Microsoft 365. What if there's an outage? What if you use Google? What if there's an outage? There's always going to be system failures like that. And it's the matter of trying to architecture backups around it. And every organization, every networking company will have different tolerances for what they can accept. Let's go back to availability. Availability is ensuring information is available within expected bounds. Now, if your company says it's okay if we're down for 5 minutes, 5 minutes is acceptable, but 10 minutes is not acceptable. What you need to be then engineering your disaster response or business continuity plan is if you're using Cloudflare and they're down for more than 5 minutes, how can you change your architecture of services to change away from Cloudflare within a 10-minute period of time? And it all depends. I'm just using these numbers as examples. Not every company will be like that. Some companies will say 1 hour is fine. Anything more than an hour, that's a problem. Some people may say a day. A day is fine. But you need to be planning for these failures. It's the same thing when people move to the cloud. Now what I'm saying is not anything new. This has been around for years. People will migrate to AWS or Azure or Google Cloud, and they'll think that they have redundancy built in because it's AWS. AWS is running all of these servers. But in reality, they've moved to one server in one availability zone at one physical location. There's no redundancy in that. The only redundancy is in power and air conditioning services and the network access. They could shut down an availability zone at any point in time. Now, these are things that cloud architects know and plan for, but you have to plan for it. What if AWS goes down? So now you're looking at multi-cloud systems, having some services on Google or Azure, some services on AWS, and being able to plan. All of this costs money. Now it goes back to the business, and you say to the business, what is the level of risk? How long can we be down? And then they say, well, we can only be down for 5 minutes. You say, great. If we need to be able to switch away from Cloudflare or AWS after 5 minutes, it's going to cost this much money. And they may say, well, we don't have that money. And you say, well, we can do it with this much money, but it means that we would be down for an hour rather than 5 minutes. And now it's the trade-off. Now it's the trade-off of risk and risk mitigation. Mitigating risk costs time, resources, human resources, and sometimes money. And you have to put it back to the company to balance that risk. And at some point, they will either adjust the risk, or they will accept the risk, or they will invest the money. And every organization is going to be different for that. But you have to look at these systems. You have to look at the architecture for networking. You have to look at the architecture for cloud providers. You have to look at the possibilities that if you're using a SaaS provider, that they may just cancel your account completely. And what happens then? Where does your data go? What legal repercussions? But even if it's legal repercussions, your data is still gone. We have to look at this. There's many countries in the world right now that are going through a de-US-ification of their services, that they're moving away from any software or services or supply chain that is dependent upon the United States, because the geopolitics is so delicate at the moment that the United States could just cut off an entire country for access for any of the services provided by American companies. And we have to be thinking about this. We have to be preparing for it. Every company is going to have a different type of relationship and different risk factor for that. But we can't just be looking at the technology. We also have to be looking at geopolitics and what's that going to mean by the services that we're using. You know, it used to be that running your own mail server was very difficult, you know, handling the spam protection, everything. So we'll just go to the cloud. We'll just give it to Microsoft. We'll give it to Google. We'll let them handle it. But if you needed to quickly, could you move away from those services? It's hard, and you have to plan for it. Business continuity planning, disaster response planning, and doing these. You can do this as a tabletop exercise as well. You can bring in people and you say, we're doing a disaster response exercise. We're not going to like unplug servers or anything like that, but we're going to sit at a table and we're going to put forward exercises. What if there's a fire? What if there's another pandemic? What if we can't come to the office? What if we lose a data center? What if, you know, machinery digs up our fiber optic cable? What if all these things happen? What if we lose our access to Microsoft? What if we lose our access to AWS? What happens then? What happens to the data that was on those servers that we cannot gain access to again? Do we have backups? Can we spin up another service and go to another provider? It's hard. It's big questions, but we have to be asking these questions because it can happen. It's currently happening to different companies in different countries around the world. It's scary, but that's where we are today. There you go. Okay, I won't hold you any longer. If anybody else wants to chat, I'm happy to chat around. Thank you very much for your time for this. Hopefully it was insightful and educational for you. And hopefully I'll see you on Thursday for the other sessions that I'm running as well.